Let us have a quick review of concepts we learned in the previous module about Gauss's law. We stated that in any closed surface, the electric flux is equivalent to the net charge inside the closed surface divided by a permittivity constant, epsilon sub 0. And we can use Gauss's law in calculating, first, the electric field if the charge distribution is provided, and second, calculate the charge distribution if the magnitude of the electric field is given. For spherical Gaussian surface, we use this formula, while for cylindrical Gaussian surface, this formula may be used. Now, let us apply this in solving word problems. A solid sphere that has a radius of 14 meters contains a total uniformly distributed positive charge of 25 microcoulombs on its surface. In this problem, we are asked to determine the electric field at 15 meters from the sphere's center. In this problem again, the radius of the sphere, the electric charge of the sphere, and the distance from the center are given. The permittivity of free space is also constant with a value of 8.85 times 10 raised to negative 12 coulomb square over Newton meter square. Let us write the working equation. Phi sub E is equal to E times A, which is equal to Q over constant. If we substitute the values, we can notice that the area is still not given in the problem, and therefore, we need to solve it first by using the formula A is equal to 4 pi times 15 meters square. Solving this, our answer will be 2,827.43 square meters. Now, let us insert this in our equation. We are interested in finding E, so we will divide our computed value of A to both sides of the equation. You can simply input this in your calculator as it is. Cancel the units, and the final answer would be 999.1 Newton per coulomb. And that is the electric field through that spherical Gaussian surface. Let us take a look in the next problem. A copper wire that has a radius of 2 mm contains a surface charge density of 5 microcoulombs per square meter. Here, we are asked to calculate the total charge present in a 2-meter long section of that copper wire and the magnitude of the electric field at a distance of 10 cm from the wire. Let us just list down again what is asked in this problem. The total charge present in 2-meter long section of the wire is the first unknown, and the second one is the electric field at a distance of 10 cm from the wire. Class, at this point, I will be pausing this video. I will let you analyze this problem again and try to solve it. When you are ready, you can click the button that appears on your screen. Okay, let us see if we have the same answer. We will list down first the given values. These are the radius of the wire, the surface charge density, the length of the wire, and the distance from the wire. The permittivity of free space, although it's not given, is a constant value. For our working equations, based on the table I presented to you in the previous lecture, you can get the value of charge by multiplying charge density with the area, and the linear charge density by finding the ratio of charge Q and L. In finding the electric field, this equation shall be used, since this is a charge in a cylindrical Gaussian surface. For point B, we are asked to calculate the electric field at a distance of 10 cm from the wire. We are interested in finding the value of linear charge density first by using the formula charge over L. Let us substitute this. Our value would be 1.25 times 10 raised to negative 5 coulomb over meter. You may notice here that we convert 10 centimeters to meters because meter is the standard unit we need for this equation. Now that we have the value of linear charge density, we can substitute the values in our working equation to find the electric field. E is equal to 1 over 2 pi times our constant value of 8.85 times 10 raised to 12 coulomb square over Newton meter square times 1.25 times 10 raised to negative 5 coulombs over meter, the value of linear charge density over distance r, which is 0.01 meter. We cancel the units, and that leaves us Newton per coulomb, which is the standard unit for electric field. Perform the indicated operation. The final answer would be 2.25 times 10 raised to 7 Newton per coulomb. Did you get this correctly? For your assignment, you can try to work on these problems. How will this be computed shall be discussed in our next synchronous session. Take a screenshot of these two problems, and again, I am encouraging you to practice answering these to prepare ourselves with more complex problems in the future. That would be all for this week's lecture of electric flux and Gauss's law. If you have questions, do not hesitate to give us a message or start a discussion both in Microsoft Teams and BBL. Again, this is Gilmar De Castro, and see you in the next video.